I wanted a dramatic entrance. I'm not sure it worked.
It sort of looked like you were on a boat or a ship and it had like rocked back and forth a little bit.
Yes, I'm on a boat or a ship. The good
Well,
ship
Eric,
office.
welcome
Hello.
to Rubber Duck Engineering. Welcome to the video frame.
How are you, Dr. Barth?
I'm doing pretty well. How are you doing?
It's been a crazy night, between required, kid-related meetings and kids having fevers, and it's been a crazy night. But otherwise, things are pretty good. So, how's your pizza career?
Oh, we made another pizza. We adjusted the timing, so now the crust is like golden brown, and we're dialing it in. We tried the new sauce, and we put too much tomato paste in the sauce. So the sauce is a little pasty, but we're dialing it in. It's getting good. We're trying again next week.
We're making pizza this next week. We did our weekly plan out tonight, but it's not going to be as fancy as yours. But
you gotta get the fancy like commercial grade flour. That's what makes it go.
Yeah, I did change my sourdough recipe this week, though. I may not have told our listeners, but I too joined the cult of pandemic sourdough this last year. But I swapped up my recipe this week, and it's working pretty well. So tonight we continue on our ecosystem adventures. If you haven't been religiously following, our VOD as of course one should, we built a ecosystem simulation of white balls and gray balls, and green balls actually too. And the white balls would eat the green balls, and the gray balls would try to eat the white balls, or rabbits and wolves, as we were calling them. And then the last couple weeks, we've been doing a bird-like object simulation called Boids, with the desire to teach our rabbits and wolves how to flock, which I think tonight is what we're going to finally do.
Should we recap and show where our current Boyd simulation is at?
Assuming I have all the buttons to push.
Yeah. So I think we realized we were having trouble last episode getting the flocking behavior that we were expecting out of the Boids. And we think it's because we're doing all this fancy quaternion math, which is telling us the orientation that all the different properties are affecting, but not the magnitude of the effect. And I think in order to get the proper behavior, we're going to have to switch over to some other data structure that can represent both orientation and magnitude.
Mm-hmm. Yes, exactly. We realized as we were discussing in the green room post-production last week that, as you said, all we're doing is we're saving the angle information, which means that we have no way to capture like how hard, how much the any one of these individual planning units matters. You probably just said the same thing, and I was only half paying attention. So,
it's our theory. We don't know. We're going to try to find out this episode if we can make it better that way.
So to show what the current Boids do, they're the little blue cylinders with little red beaks, I guess we could call them. And then we have the ability to turn on and off the various different behaviors. So there I just turned off separation. I could turn off the homing behavior and they'll stop trying to come towards zero. I can turn off the alignment behavior and then they won't try to all align with each other. They'll just end up clustering. So, yeah. So shall we fix our code?
Let's try.
I agree that it doesn't work until it works, but I'm pretty confident that our theory is correct. So let's close up some windows here.
Well, the other thing I noticed, I was looking at some example code for Boids.
Mm-hmm.
At least in that example code, they were applying these different properties as accelerations on the angle, as opposed to we're applying them as we're trying to set the angle to that value. So that may be another factor that we want to change at the same time.
Okay. Those last words made me worry because I want to try and change one thing at a time. But
Well, okay, let's do one at a time and see. But if this doesn't work, we have a second thing in our bag of tricks to try to pull out.
all right, so all right, yeah. So which one should we do first? I don't know that it matters.
Let's do plan alignment. This looks like the simplest one.
All right, so we want to end up. Oh, first of all, we need to move ourselves. Go ahead.
I was just checking. So the nearby objects do not include ourselves. So we've already been removed from the set of nearby objects.
Okay. Just getting set up here. So this is our other Boids rotation.
Right. So we want to look at its.
Do we want to align more with closer objects than further objects?
I don't think so. I can go look at the. Do you want to go pull up the sample code on your screen? I don't know if you have it handy.
Mm-hmm. I don't think I do, but.
I didn't actually find it from Wikipedia. I just searched for Boyd's example.
Yeah. Oh, it's so pretty. I want my rabbits to do that. New flock, add Boyd, draw, flock, run. Sure, yeah, but this is what I want. You're right.
So somewhere here there'll be some alignment function.
Cohesion, alignment. From a nearby Boyd in the system, calculate the average velocity.
Yeah, so it's taking a displacement vector.
Mm-hmm.
That's just the filtering and other dot velocity. So velocity, do we have velocity as a? We have it as a float on Boyd. So we need to take its direction.
Yeah, I mean you can
multiply
just
it by the velocity,
which is just Boyd dot transform dot forward times Boyd dot velocity, right?
Okay.
That is the velocity vector.
Yeah, I think that's correct.
I mean, we could even do it this way if you wanted, right? You could do vector tree velocity vector. That makes that code cleaner. I don't know how often we're going to need this, if at all.
Do we need to say like a getter or something somewhere?
Yeah, we could. It's like get something like that. I don't C# getters very well.
Oh, I can research that.
I had to do it once. I've not done it since. I can also just add these, and then it'll be happy. So I'm sorry. So this was taking the velocities. Yeah, the velocity vectors right here. And
oh, you just made it a function.
Okay. And summing them all up. Yeah, I mean, we could easily convert it back.
So right, we should actually learn C#, but
what? That's like cheating. Oh, you're right. I'm supposed to give it really strong camels.
Okay, so let's keep reading this. So,
What did you say? So average doesn't need to be computed here. So we just do sum plus equals Boyd dot get velocity. Oh, I'd have to get component. Okay. retreating. That's even less. Oh, except Boid.velocity is not going to help either. They do need to get component. Oh, that's so lame.
Mm-hmm.
Ugh. Okay. Boid. This is geo. Game object is equal to get component. Void. Sum plus equals. Did I confuse this sufficiently?
Yeah, I think that's good.
And then average just needs to be divided by length. What? Is it length?
That's count with a big key,
Why not?
big count. Yeah, so that's so then the example code also has this in it. But after they do this, so this is like the average, right?
Oh yeah, totally. We do have to normalize it.
Okay.
Do we?
Well, I'm trying to figure what this does. So this normalizes it and then applies some max speed property. And then the steer vector is the thing that we're missing. So the thing we want to return here is somehow this like steer vector.
Which is sum minus our own velocity. Like that's the delta.
That's the delta. Yeah,
Velocity.
desired minus velocity. Makes sense. That's the correction that we should apply to our velocity.
Okay. And then
So we don't have these max speed and max force properties.
Oh, I see.
Which we'll need to figure out. But
I don't understand what's the I mean, the max speed can just be our speed. So it's just normalizing it not at 1, but normalizing it at the expected speed. Right? Because we could be like way off of, or we're not operating in the unit circle. We could actually just return it normalized, but then we'd have to remember to multiply it by our expected velocity. Yeah. Okay. This makes total sense to me. I'm not explaining myself very well. But so if we want to calculate a like difference vector, we have to do that in the like same coordinates. Otherwise, we're going to have a speed change in there too, which we don't need.
Oh, I see. Okay.
Right. So we're taking average and we're normalizing it.
Okay.
And then we're multiplying it times like our speed.
Okay.
So this is, and then so this is not really average. This is averaged.
Right. So in their terminology, this would be desired. We desire to keep our current velocity in that direction.
Yeah, and then we want our steering vector 3. This is our like delta or whatever. Steer is equal to desired minus our current.
Right, get velocity vector. Okay. Yep, we just return that. Like these limiting factors, we can do just.
I wonder, like, why do we even have velocity in this whole time? Like, why aren't we just operating always on normalized vectors?
We could do that. Like, basically, you could take the velocity out here, take our transform forward here, and then return steer times velocity.
Well, you have to take it out of here too, don't you?
Well, for there, if they're going at, like, imagine the voids are going at different velocities.
Mm-hmm.
then somehow we're weighting their contributions to the alignment based on their velocities.
Which doesn't make a lot of sense. Like, this is why I would think you would just normalize for each Boid.
Okay, so we can do that. So then we can skip the get component here and just say transform
forward. Is it dot normalized then?
You still want to normalize it because after you add it all together and divide by the count, it's going to have some crazy unknown magnitude. Like the more they're aligned, the more their magnitude, the larger magnitude you have.
Yeah.
So this makes sense. And then
steer.
The question is, do you want to multiply by the velocity here?
Because this is like our desired vector. This is where we think we should be pointed.
I don't know. We can try it. Like, why don't we make a note here that like we're not sure to fully like I wish there was more of a specification of what this was supposed to do. Like one of the things I liked about the Game of Life is there were very clear rules. Like here's the spec, here's your test cases. Whereas this thing, it's like the Wikipedia article is like, well, in general, you should try to align with your nearby things. And so it's less clear to me exactly what that means.
It's interesting because my initial instinct in responding to that was like, oh, I kind of enjoy that we get to like sprinkle in our own special flavor. But then I also was thinking back this last week about some of like my most enjoyable times in my career. And some of them were when I was working on Chrome with you. And I remember particularly fondly working on the HTML5 parser. And I think there were two things about that experience that I really loved. One of which was that we were working on something that affected whatever billions of people. But also it was like, it was very clear what, shaped hole it needed to fit in.
Yeah, to me, there's a distinction between like the what and the how. So to me, the like what is like a PM kind of question. Like what was it should we build, right? That's like a product question. But the how to me is the engineering question. Like how can we do that thing the best way or the most robust way? And you always find that like even like very, very precise specifications, there's still things that aren't specified. And like so this come up. I remember particularly when we were working on the pop-up menu in material design. And the pop-up menu in material design is this awesome animation where it like expands and comes down and like materializes. And then we asked the designers that, okay, well, what happens if the user taps where the button is going to be when the animation finishes? What should happen? Should it, like, if you were actually physically animating all this stuff, that would end up dismissing the menu, which didn't quite seem like the right thing. And I still remember that the answer we got back from the designers was, if people are clicking there, we should just increase the speed of the animation. And I'm like, no, you don't get it. I've slowed down the animation by a factor of 100 so that I can poke all of the corner cases. If you speed up the animation, I'll just slow it down by a factor of 500 so that I can poke all the corner cases.
Oh. Yeah. Now my brain is off going about what it should do. I think it should ignore the click.
What we made it do is we made it select the menu item as if the animation had finished. Because the way the animation is designed, the items never move. So they never jump away from your finger. So the theory is if you have good muscle memory and you like know exactly where the button is going to be, you can hit the menu, click the button, and then just be done with it.
Okay. Makes sense. All right. So how do we integrate our new alignment vector?
Well, why don't we keep doing this? Why don't we convert them all to vectors, and then we can look at how to integrate them.
I was trying to limit the harm from our from the bomb we're letting off in our code here.
Well, the harm is really in Git, right? Like we have a Git commit of the thing that we can always like stash, right? Like,
yeah. Okay. There's also an MVP question, like how is it going to fail when we do that? But okay, fine. We keep going. All right, so we do separation next?
Sure. Oh, separation was the hardest one. But
all
sure,
right, so let's do
it
next.
Okay.
We did like a whole episode on separation.
Yes.
Cohesion.
So I'm going to paste the sample code for cohesion up at the top.
Oh, okay.
We don't have to flip between windows.
Start with an empty vector. Accumulate all positions. Sure. What is dist?
Distance, I presume. This is their like. They don't have awesome C# subtraction.
Sure. If
this is just filtering. So we're just trying to compute the average position of all the nearby. Add the position.
Okay. And then we're steering towards it. And then they have some seek.
Seek. Yeah.
So
okay.
what did we do here?
So we have the average position. So we just need seek actually. So we don't need any of this. Find their seek function.
And seek is just like look at, but with a
yeah. So here is seek.
Desired.
So let's get rid of this. So we just add up all the stuff. Here's your target. So we take our delta from us to the position. So that's this. This is desired.
Scale. And they operate in maximum speed coordinates, which is like whatever. They have their scaled unit circle.
Okay. And then they compute the same steering vector as before. So it's just the same equation from this previous one. That was
okay.
Yeah.
Well, oh, I see. Because it, yeah, it's this part. The steer. I see.
Yeah,
okay.
Oops. We're just going to copy our code from up here.
Average position. So we have it exactly right.
Here we don't have to multiply. So here it makes sense to multiply this by the velocity.
Well, then maybe it should always make sense.
The desired is, so, right. Do they normalize this? They normalize it, right. I see, because if you don't normalize it, this vector here will get you to the middle in one step.
Mm-hmm.
So you want this normalized so you don't go crazy. Right, so you have the same question here. You still have this weird multiplication by the velocity at the end.
Well, they just are always they're moving in a unit space. They just have chosen their unit space to be at max velocity. They're go ahead.
Let's say when we do all of these, we may find they all have multiplied by velocity, and we can just take it all out.
Sure.
This makes sense, right? So you try to find out where the average sum is. You take what it would take to get there from here. Yep. You say, let's not do it all at once. Let's figure out how much to steer. Yeah. Okay.
Well, let's not do it all at once, but rather just take. This is just the vector along the unit circle minus transform forward. That doesn't. Oh, because transform forward is in unit circle. No, it's not. Oh, yeah, it is. Of course it is.
Right. So I think it actually would be more parallel with our other code if we did this.
Mm-hmm.
Right. Because now our desired is in the same units as our forward. Mm-hmm. We can figure out our steer. And then we have this funny multiplication that we don't quite understand.
Okay. Yeah. All right. Shall we attempt plan separation?
Sure.
Shall we look at what they did?
Yeah, I can paste it in if you'd like. Plan separation. Yep, I'm on it.
Right. Desired separation. Yeah, they have some fixed tail. Mm-hmm. We're working towards a steer vector. In the system. Okay.
Right, but we've already filtered the Boids by position.
Mm-hmm. Pointing away from that neighbor, just like we did. Normalize weight by distance.
So diff
Oh, interesting.
Delta normalized.
Mm-hmm.
Okay. Divided by distance. Add it to the steering vector. So they add it directly. So we don't have the steering vector.
Yeah, they're using their same vector 3 steer. Yeah, they're just accumulating in. Don't need this.
So this is steer here.
I need this, yeah.
Look at this.
It's not clear that we need to count either.
Well, let's see. So they have this. So they
because they don't ever divide at the end.
Well, they divide here, right? They say if count is greater than 0, then
I see.
steer equals steer by count.
Yeah, you just do it. C# will do it with the thingies.
But yeah, C# awesome.
Has operator overloading like any language should, maybe. Does Dart have operator overloading? It must. Yeah, it does. Just
Okay,
not as many as C#.
C# really goes operator crazy. Okay, we did all that.
Well, C++ did too.
So now, if the steer magnitude is greater than 0, then normalize max speed, subtract our velocity. So this is not really the steering velocity. This is like the desired velocity. Okay. Figure out your desired velocity. And then you do the same calculation here.
Yeah. Mm-hmm. Yeah. Looks like it might work.
Well, I think we're not handling the 0 case correctly. Like, this is going to, like, what's the point of this? What's the point of dividing by the count and then normalizing it? That doesn't make any sense.
All right, so
I think if count equals 0, we're just going to return new vector 3 here. Because we're just like, sorry, no interesting steering to do.
Mm-hmm.
Otherwise, we take our sum.
It's not exactly, it's like a weighted sum, but yeah.
Yeah. I guess if you go back to line 59, it's the same sort of thing, right? We take this sum, we divide it by the count, and then we normalize it. Like, it's like division doesn't make any sense to me.
The dividing by the count?
Yeah. Because you're just going to normalize it right afterwards. Like, what's the point?
Because the dividing by the count does not change the angle, only the magnitude.
Right. Yeah, it's just a scalar, right? It's just going to scale.
Okay. Yeah, I believe you. So then the divide by count doesn't do anything if we're just going to normalize.
That's fine. So then here, so these things all end up being very parallel to each other.
Mm-hmm.
I guess it's good. This is desired here now.
I lost you where you went here.
Oh, sorry, I'm on line 100. Okay.
Yeah.
All right, now we're back to the problem that you were.
My instinct is to, yeah. My instinct is to wire it up and try it, but obviously we have to wire it up here.
Yeah, so now we need to figure out how to combine it.
Well, we can see what they did.
Yeah, so the way they combine it is, here's their combination function. I'll paste it in here. I'll update. They get all three values.
Mm-hmm.
They weight them.
And then what's their apply force?
So applied force.
Acceleration, add force. So what's acceleration? Update. Velocity, add acceleration. Velocity limit to max speed. Oh.
Well, then they just reset it to 0 every cycle.
Yeah, it's this acceleration for this frame. Or it's the
Okay, so we can just add it. We can just add it to the to our velocity, right?
We are storing things separately. The velocity is our scalar, and the rotation is our. We're storing our velocity vector in two pieces.
Sort of, but look down here on line 155. Like that's where we're doing this, right?
Mm-hmm. So
I think we need to pull out this calculation.
Well, we also need to have the rotate part, right? We have to. We can compute it. We can sum these all up, but then we have to split it. At least the way that we're currently applying it.
Well, let's compute our acceleration vector.
Oh, I see. You're saying we could maybe just use the translate.
I don't fully know what we're going to do, but let's try it. I'm going to get rid of the homing for now, because homing is still in quaternions.
Mm-hmm.
So we're going to take our acceleration plus equals plan alignment.
Mm-hmm. Oh. Hello, maybe Hal.
Hi, maybe Hal. How you doing?
Happy Thursday.
And then do we want to put in this 1.5 multiplier for the
sure
separation?
Why not? I mean, we did something similar in our previous.
All right. So now we need to figure out how to apply our acceleration.
Yeah, so the way we're currently doing it is we would have to normalize it and then rotate towards that normalized, right?
No.
No.
Well, we could take our velocity vector. Get velocity vector plus our acceleration, right? Times delta time. So we need to factor in delta time in here somehow.
I think we do that. Okay.
Because over some amount of time, we're going to change the velocity vector. This is our new velocity vector.
Mm-hmm.
And then we need to apply that to our position. So translate by we don't want to do this. This is what we don't want to do. We just want to translate.
We do need to rotate ourselves, right? Like there's a rotation in that velocity vector.
Right. We need to, I see, because we want to.
We always want to be going straight forward.
Right. If we didn't have a nose, we could just move ourselves. Correct. But we want to rotate towards the velocity vector.
And we can split this, right? That's what normalize does, right? Am I remembering that when you do normalize, then now you have a rotation vector?
You have a unit vector, yeah.
You have a unit vector, which then you could put into quaternion that. Euler angles, right?
Well, this is this look at thing, right? We want to look at that.
Yeah, I don't remember what rotate towards does.
All right, I think we want to set the. Let's look at quaternion look at again.
Yeah, I could imagine a bunch of ways that we do this. Right? You could imagine you just do transform dot rotation is equal to, is this Euler angles or this is a quaternion, right? You could just do quaternion. What's this look rotation thing? Anyways, you could just do Euler angles. And then new velocity normalize. That should do it. I don't know that that's a good way to do it, but that'll do it.
I don't think the Euler angles is correct. So Euler angles are going to treat, like, this is a vector that's pointing from where we are to where we want to be looking, right?
Oh, yes, you're right.
The Euler angles are like the out of 360 degrees.
Mm-hmm.
We had this before.
I'm also certain there's just like a shorthand in Unity for this. I just don't know what it is off the top of my head.
Yeah, transform.look at, I think, is what we're going for here.
Okay.
We want to
look at take I guess that's fine. As long as it's look at in like local coordinates.
But we take our position plus a new velocity vector. It doesn't matter how much what the multiplier is.
Yeah.
Go look at that, and then move forward by that much.
Sure. I'm sure there's a cleaner way to express this in Unity, but that looks like it should work.
We need to factor in the time delta here somehow.
We do, right here.
But this is acceleration per unit time. So like if the frames are really far apart, then we should move the velocity vector a lot. If they're really close together, we should only move it a little bit. So I think that means we should multiply by time.
What is this velocity here? Oh, that's our existing one.
Yeah. Right. So we could pull the. So I think all this would look a lot prettier if we, in each of these planning steps, we didn't multiply by velocity. Let's take that out. And then they're just going to give us steering directions. Okay. And then now we can put the velocity here.
But what unit space is the steering directions in? It's not on the unit circle.
It's not on the unit circle. They're different. They're in some sort of normalized, like relative space. So this is like.
Yeah, these are like velocity adjustments.
Yeah,
acceleration probably really. Go ahead.
Yeah, these two velocities could be different. This is like how much do you want to? This is like our old rotation rate. Rotating rate. Really what that is. In different units, but should we try this?
Sure.
I don't think it's
I have
quite.
to stare at it a little bit more, but
yeah, I think it's not quite.
We'll try it. Compiler errors.
Oh noes. F. You put the F in, but then it somehow disappeared.
I applied vector 3 and double. Why not?
You just need Fs.
Just need Fs. More Fs.
More Fs.
Oh, you're right. More Fs.
The Fs will continue until morale improves.
C sharp. How we love thee. Okay. It kind of looks like it's doing the right thing. Except where's the cohesion? That feels like it's missing cohesion to me.
There's the ones on the edge are kind of moving towards the middle.
Let's add back homing so they stay. So homing is basically, this is where like you want things like a seek function, right? Because homing is basically this. Right? Am I crazy?
No, you're totally right. And then, yeah.
And then I don't remember where.
We just do this. Acceleration plus equals steer. Come back home. Come home.
Oh. That's fascinating. Like the flock turned.
Well, I think what happens is once it it's normalized.
It's not clear to me that this is like entirely right. Also, the steering rate seems slow. No, it's not that slow.
I think this looks pretty good.
I think this is good enough to give this to rabbits, right?
Yeah, okay, so we switch over to integration mode.
In our last 10 minutes. I think this is good enough.
All right.
I should make a commit. I haven't made a commit in a long time.
Oh, so our strategy of git stashing to go back to the previous working thing might not have actually. We were working with that on it. Oh, we have a question from Voncorn.
A question: do they collide as well? The rabbits or boids, they have no. They don't have what's that? The collision box thing called? They don't exist in space. They're just like drawn.
So I think they don't collide. They can overlap with each other.
Hello, Greg. Nice to meet you. So yes, they can overlap with each other, Greg. And also, in case anyone is new here, please remember, we have no idea what we're doing. Okay, in honor of having a second viewer, I think we should commit. This is so not correct, but like accumulated work of the last few episodes.
Various fixes and bug fixes. Yes. It's like the my favorite update message on all my phone apps. It's like, we fixed a bunch of bugs, we made things faster. I'm sure you'll like it. Then you update it, and they like change the UI completely. It's like a different app. It's now like about shopping.
There we go. Whatever. That's not anyone taking notes at home. That is not how you use Git. Certainly not if you want to work with people collaboratively on other projects.
At least not if you want to continue working with that.
It's funny, over the Christmas break, I was so glad that we relaxed the rule that I could hack on this at other times. And then since life has picked back up, I've had zero time. And so Unity just gets backgrounded. This computer gets dusted off occasionally to play a game or two with my kid, and that's it. So otherwise, it does not get any love anymore. Okay, so next is to figure out how to add this back.
Right. So I think I don't know what happens when we just add the script to the.
I don't know either. Like we have whole planning. Like the animals know how to plan.
I think we somehow need a. Well, let's just try it. But I think we're going to need some kind of control knob for this behavior to like turn it all the way on or to turn it all the way off.
I agree, because it's only like during wander time. Because otherwise, in our update, yeah, like we have these like different. So it would be like in the like do wander update or something like that. We want to run the Boid stuff, or we tell it to take over.
Right. So maybe what we should do is instead of doing the instead of hooking update, maybe we should just make this a do Boid update, and then the other behavior can call it during update if it wants it to happen.
Okay. Are you still there?
Yeah. Oh, sorry. Did I pause?
No, one of my my control computer actually ran out of battery, so we'll see how I do shutting down the computer, shutting down the stream.
I just renamed it so that it's not. Maybe there's a more idiomatic way of doing that in Unity.
I mean, certainly. So we can teach the animal about the Boid behavior and like know how to turn it on and off, turn it off. In fact, we do some of that, or I started to do that with the agent.
Oh, you know what? Each component has an enabled state, so we can just enable the Boid component.
Whoa!
When we want it to go, and disable it when we don't.
Okay. And since we don't need any of this, okay, sure, let's try it.
So I think in the editor we need to associate the script with the object.
Okay. Yeah, so we gotta go back to editor land. We have to leave our little Boid editor here. Maybe I should commit again. Since we have all this junk.
Oh, what was all this? Those are things that...
Save the Boids.
Again, plus.
If you're following at home, this is not how you use Git. Okay, or should. Okay, so we could go back to our sample scene.
Sample scene is the main scene where we did all the work.
The main scene where we did all the work. We gave it a great name, I thought. A+ for naming. And now we want to edit our prefabs. Also, I can't see the chat with my control computer down, so if it's just overflowing with inspirational comments, you'll have to fill us in.
The last comment is that there was a lull from Von Korn. Which
appreciate your...
I find inspiring.
I appreciate that Greg has a sense of humor. Okay, so I added Boid here.
To which
to the I don't know, Predator. Why did I give it to the Predator?
Oh, why not?
Sure. Should we give it to the Prey too?
Sure. Let's go nuts.
Go big or go home. All right. We should maybe give them a little more velocity.
Oh yeah.
Oh, this is
they
so
had
hacky.
They had a wander velocity before, right?
And now we're going to be setting it separately on a... I think the way that we currently set it is it evolves.
I see.
So it's like set way over here in this other object. This is our best design ever. Right here. Initial prey trait, speed. And wander speed multiplier. I think... Okay. Oh, yeah, because we turned off the wander. Oh, my God. Okay.
That's fine. Let's just set it. So the prey should have a velocity of 4 and the predator should have a velocity of 2.
Okay. Velocity of 2. You said the predator had a velocity of 4?
Yeah. Let's give them some... The turning rate we're not using currently.
Okay.
That's cool.
I thought we did. What's the vision rate? Oh, vision rate is like
What? Yeah, probably 20. I don't know.
pardon our spaghetti. Our amazing spaghetti.
Maybe
Okay.
30 for the predator, since that's what we're using elsewhere.
Sure. Okay, and so now the idea was that we were going to, in our animal, so we can also require a component up here and grab the. Oh wow! I have this nav mesh agent. No, I want Boyd. Did I really have a nav mesh agent still?
Yeah, I think we were trying to do nav meshes, but we didn't succeed at that one.
Yeah, I remember trying and failing. I'm surprised that it wasn't yelling at me. But maybe we haven't run this version. Okay. And then how are we going to enable disable?
Yeah, so somewhere in the planning of animal, when we decide what to do.
So plan once. Plan once. Okay. And then it's like right at the end here, I think. Yeah, we don't have any early returns. So it's like if m plan equal to objective.wander, then we do
It's even simpler to that. We just said, yeah.
Component void. You said enabled?
Mm-hmm. You just set it to this.
Go for it. Make it so. Sold.
I wonder if that'll work. We could try it.
Sure, why not? Let's run the simulation. See if it blows up. We got some shaken rabbits. That may be our wander speed multiplier. Yeah, so this is the wander. We need to.
Oh, we don't want to do wander anymore. Like our own wander, we want to give up on.
Yep. This thing.
Yeah.
We just can.
They were kind of dancing, the rabbits.
Yeah, that was the wander stuff. I think it's working.
You think so?
I have no ability to tell.
We need to simplify the equation to see if it's working.
We have to I think we have to throw their metabolism way down or something. Help them to these poor little rabbits have some attention problems.
Well, they just get hungry.
Yeah, they get hungry or happy to see each other. Wow, that one is going so slow. Oh, and then it sped up so much.
So we lose all the predators? Yeah, we lost all the predators.
I think that's working. Whoa, hello. It was hungry. Yeah, the speed multipliers are so strange. Look at that. Yeah, they zip across when they're hungry or something?
When they go into food mode, they totally go turbo.
Oh, actually, maybe it's not. Oh, you know why? Because, so we also need to in plan once. Where is it? This. We need, I will use word shortly. Boyd, var Boyd. Need to do void.enabled. We also need void.velocity is equal to m traits speed.
Oh, so we get the evolve velocity.
Correct. Because otherwise, when they were wandering, they were just at whatever.
Oh, I see. But once they learn how to be super fast hunters, it should affect their
Correct.
wandering speed too. That makes total sense.
And so that's why it was looking so strange. Yeah, it's totally working. Look at that flocking behavior. We have flocking rabbits. Now, why are they pausing?
Why are they pausing? That's a good question. Okay, that definitely solved the going really slow during their flocking phase.
Yeah, you can totally see them flocking. Like, and I love the like nice continuous adjustment that the flocking behavior has for them.
Yeah, the wander was always terrible. They would always just like randomly move
Sure.
around. Like,
I like that they also have a homing behavior now too as part of the wander.
so they don't go too far off range.
Wow, they get zippy.
Well, they gotta get those cabbages.
I love this. I really enjoy this sort of simulation-y stuff.
I feel like we took a long walk to get the flocking behavior, and like the effect on the simulation is pretty subtle, but I think it actually makes it like a big difference.
Yeah, it's way nicer. Okay. So is that the show?
Yeah, they should declare victory.
Let me see if I can get my command and control module back.
Cool. He thinks it's looking good, so
I think it's great. Let's see. Enter broadcast studio. Oh, done.
Yeah, thank you everyone who's joining us live in the chat. It's really, really great to have folks to talk with.
Yeah, it was nice to have you, Greg. I hope you come back. And nice to see you, maybe Hal. And otherwise, Dr. Barth, I had a lot of fun. I'm glad that we actually got our flocking behavior all wired in.
Yeah, we did it. Yay!
I wish you lots of luck with your pizza. And otherwise, I'll see you next Thursday.
Sounds good. See you next week, Eric.
Good night.